Hello everyone. Thanks all for coming. It's a really great pleasure to be at Meta and share some of the work I've been doing as a part of the MethaneSAT mission. Today I will introduce a new automatic methane plume masking method that I developed for methane point sources detection. This method is based on wavelet transform image processing, and throughout the talk, I will show you some interesting results from applying it to both MethaneSAT and MethaneAIR data. But before I get started, just want to emphasize that this is very much a team effort. So the work I will present today reflects contribution from the whole MethaneSAT and MethaneAIR science and engineering team. So yeah, a lot of credit here go to my colleagues. So for those of you who may not be very familiar with MethaneSAT or MethaneAIR, I will start with a quick introduction to the mission and the data used in this study. So MethaneSAT was operational from March 2024 to June 2025. Unfortunately, we have lost contact with it since then, but during its operational period, it collected a valuable data set that demonstrated its unique position in the world of methane satellites. So our goal here is to categorize methane from both dispersed area emissions and discrete point sources, covering more than 80% of global oil and gas production. So the left table here shows the key instrument characteristics. So MethaneSAT has two wavelength bands, an O2 band and a combined CH4/CO2 band. Both these bands have sub-nanometer spectral resolution. The spectral resolution is 100 meter across track times 400 meter along track, which is, moderate compared to typical point source imagers. Here we use the CO2 proxy method for methane retrieval, as shown in the figure in the lower right. So CO2 proxy basically uses CO2 as reference gas to infer methane concentrations. And what's nice about this method is that CO2 and CH4 are in nearby spectral bands, so the errors due to scattering and aerosols tend to largely cancel out. And the retrieval product is the full column concentrations of atmospheric methane. And another important aspect of MethaneSAT is that it focuses on targeted regions, primarily oil and gas basins, so its spatial coverage is selective. So this map shows our global targets. You can see that each target varies somewhat in size depending on the latitude, but the typical scene here is about 220 by 220 kilometers. So what we're looking at is a fairly large area, which allows us to capture both area emissions and individual plumes within a single scene. And the revisit time for each target ranges from a few days to several weeks. And next is MethaneAIR. MethaneAIR is an airborne demonstrator of MethaneSAT. It shares the same scientific goal, which is detecting both area sources and point sources, but it mainly focuses on the major oil and gas basins in the United States. So in this map, the highlighted regions with these white borders show the target basins, and the smaller colored polygons represent individual MethaneAIR flights. So each flight typically follows a Zamboni-style pattern to cover the region. So the pattern here can be seen in the lower left image. And the spectral resolution is much finer than MethaneSAT, which is about 5 meters across track by 25 meters along track. And here we use the same CO2 proxy retrieval in a similar wavelength range to derive methane concentrations. So here are two figures showing the level 3 concentration maps of MethaneSAT and MethaneAIR. The pixel size here is upscaled. So for MethaneAIR is 10 by 10 meters, and for MethaneSAT is 45 by 45 meters. And you can clearly see both the point sources and the area emissions from these two maps. So for example, in the left figure, this is a MethaneSAT scene. You can see the left here, if you can see my cursor. So this is a plume. And interestingly, because of MethaneSAT's sensitivity and its large spatial coverage, we often see these plumes be tracked tens of kilometers downwind. And also, these border areas in the lower part of the image are probably dispersed area emissions that are below our detection limit. And similarly, in the methane methane concentration map on the right, you can also see a plume here. And if you zoom into this region, you can actually capture multiple smaller plumes in this area. And this southern part of the image is also probably a wide area of diffuse emissions that below our detection limit. Yeah, and interestingly, if you see this small area of elevated enhancements, so in our study, we tend now to take this area as the point sources because in our definition of a discrete point source, the plume requires to be source localizable, meaning that it either has a smaller clump with elevated enhancements within the plume to indicate the source location, or its shape aligns well with the wind direction so that we can, infer the upwind end of the plume as the source location. So because of this definition, examples like this smaller area or the other, broader area will all be considered as dispersed area sources. And for those emissions, we use inverse modeling to create an emission map of these. And the map has 4 by 4 kilometers resolution. So because of the scope of this study, this talk will just focus on the discrete point sources, but happy to answer any questions related to the area sources. Okay, next, I will introduce the two point source detection methods that we currently run in parallel. So the divergence integral method shown on the left is a purely physics-based approach. It basically applies Gauss's theorem to calculate the integral of flux divergence of a closed surface. And by divergence, I mean the flux intensity representing how much emissions are either entering or leaving a given point. So by integrating such quantity, we can generate a flux map. Then the plumes are identified using both the flux map and the original methane concentration map. On the contrary, the wavelet method shown on the right is purely image processing driven. So what it does is that it applies discrete wavelet transform to the concentration map to create a denoised version of the image. So instead of a flux map, the main output here is a cleaner, denoised concentration image, and plume masking is done through thresholding on that image. So the input data for both methods is the level 3 full scene methane concentration map. The map is subjected to some pixel screening in upstream processing, meaning that there can be some missing data due to, for example, the cloud coverage screening, water surface screening, etc. And subsequent steps are for both methods, including the plume masking by thresholding and filtering, and then determining the source location as the farthest upwind end of the plume. Okay, so some of you may already start to wonder, like up to this point, I haven't really explained what a wavelet transform is. So let me just take a moment to walk through the basic idea using the illustrations here. So let's say we have a matrix X, which you can think of as our concentration map. We can also define two types of filters, a low-pass filter and a high-pass filter. So a low-pass filter keeps the smooth, slowly varying components of the signal. In other words, it keeps the large-scale structure of the image, while a high-pass filter extracts the rapid changes, such as edges and noise. So now I can first apply the low-pass filter along the columns of my matrix X, followed by downsampling. And then I can apply the low-pass filter again along the columns, also followed by downsampling. So the resulting matrix here, its size is a quarter the size of my original input X. And similarly, I can apply the low-pass filter along the rows and then the high-pass filter along the columns to get another matrix with the same size as my previous one. Or I can do this, the other way around. And finally, I can apply the high-pass filter along both rows and columns. So in the end, I have four resulting matrices, which can be presented this way. And among these four matrices, the upper left one, which is the one that's formed by running the low-pass filter along both rows and columns. So this one maintains the low-frequency structure of my input matrix X. So we name these matrix as our approximation. And the rest three matrices here, they represent the details, or say the high frequency information, including the horizontal details, vertical details, and diagonal details. So this may sound a little bit too abstract, so I added a figure, an image example here. So just know that this example does not show the original image or the matrix X. What it shows here is the four sub-matrices after the wavelet transfer. So again, the upper left image here is our approximation, meaning that it captures the large-scale structure of the original image, except that it's now with much coarser spatial resolution. And the upper right image here is my horizontal detail matrix. And I'm not sure if you can see it clearly in your screen, but here I can see some horizontal edges of the squares here. Similarly, this matrix captures many vertical edges, as is our vertical detail matrix. And the lower right one captures most of the diagonal structures and the noise. Okay, so to summarize, a 2D wavelet, discrete wavelet transform can do a pretty good job in separating the low frequency signals and high frequency signals from a given image. And that is exactly why it is very useful for our problem, because we want to suppress the background noise from our concentration map so that we can, enhance our plume structure so that it's easier for us to mask out the plume from a concentration map. So exactly how do we apply the wavelet transform to our problem? So this slide shows the main workflow here. So we can start with the original figure image shown in the figure A. So one challenge we observe here is that the plume pixels are not uniform compared to the previous image example I showed in the earlier slide. It's because the concentration typically decreases along the wind direction. In other words, the plume is not a purely low frequency feature. So as a first step, we apply a simple pre-processing, meaning that we set a pixel value threshold, and any pixel above that threshold is reassigned to the maximum value of the image, as shown here in figure B. So in figure B, now the plume pixels are all consistent, but we also see that some background pixels are raised as well. But that's okay as long as those pixels they still vary rapidly in space. These are still high frequencies, so they can be easily removed in the next step. Okay, so now next is the core step of the method, which is shown in the bottom panel here. So we call this as a multi-level wavelet transfer, meaning that we do not just apply the wavelet transform once, we apply it recursively to the approximation component of my results. And that creates a multi-scale decomposition of the image so that the structures are separated at different spatial scales. So after L levels of wavelet transform, I get something like this. And then I did some modifications of my results by setting all the approximations to 0, meaning that now I want to get rid of all the approximation and just preserve the details. And then I use the inverse wavelet transform to create a reconstructed image with the same size as my input. And this is something like in figure C. So the reconstructed image, because it only keeps the high frequencies, so it contains most of the background noise and some edge information of my plume. So next, what we did is that we subtract this reconstructed image from the input to get figure D. And clearly, compared to my original image, figure D already have most of the background noise removed, and also the plume structure is greatly enhanced. And finally, we apply some additional denoising and filtering to get the final output in figure E. Okay, so one quick note here is that the pixel values in the denoised image here no longer retain their physical meaning. So we just use the denoised image to guide our plume detection, but the actual masking is applied back to the original concentration image. So more specifically, we apply the pixel value thresholds and clump size thresholds to the denoised image. And then we use the 8 connectivity algorithm to identify connected regions as our plume candidates. So the 2 figures on the upper right shows the workflow of our plume masking. And after generating these initial masks, we apply a series of additional filtering steps. So first, we want to see the concentrations, whether the concentrations within the plume make sense or not. So we check whether the plume contains smaller clumps of higher concentrations, or in other words, hotspots that commonly appear within the plume. And the plumes with no such hotspots will be filtered out. And for those who have such hotspots, we will secondly observe the plume's shape, because some masks generated by the wavelet method can have shapes that extend and curl unnaturally from the center, and these are apparently not physically realistic. So we quantify the degree of such curling and filter out those that don't make sense. And lastly, we compare the major axis direction of each plume derived from its shape with the wind direction information from meteorological data. So overall, these filtering steps are designed to ensure that the detected plumes are not just statistically significant, but also physically consistent. And my last slide in the methods part, before I jump into the results, is a quick introduction of our quantification method. So currently, we go back to the divergence integral method to calculate fluxes. Like I said before, the DI method here, it calculates the integral of flux divergence of a closed surface, or in other words, it converts concentration enhancements into fluxes given the location of the plume and the wind information. Specifically, the way we implement this is that starting from the plume origin, we draw a series of rectangles around the source. These are what we call growing boxes. Then for each box, we aggregate the concentration enhancements along the box boundary and apply DI to estimate the flux. And finally, we take the average of valid fluxes derived from all boxes as our final flux estimate. So the performance of this method has already been validated in previous control release tests using MethaneAIR, And the right figure here just shows the methane air with a DI quantification achieved pretty good accuracy compared to the ground truths. Okay, so now is the results part. So first, we apply the wavelet method to methane air data from 2021 to 2023, and we compare our results with those from the DI detection method. And those results were already published in Warren et al. In 2025. So a quick note here is that because we used the same quantification method in two studies, we can therefore directly compare the results in terms of flux. That's why we create the left figure, which is a histogram plot showing the number of identified plumes in different flux bins. Here, each bin has a weight of 200 kilograms per hour. So each bar is stacked by detection method represented by different colors. So for example, this bar here is between 800 to 1000 kilograms per hour. It shows that we have 6 plumes detected by the DI method, 33 by both methods, and 12 detected by the wavelet method only. So overall, the wavelet method identifies 262 additional plumes compared to the DI method. And most of these additional detections fall in the lower flux range, between 0 and 1000 kilograms per hour. And because of these additional detections, the peak of the distribution, or in other words, the most frequently observed flux rates, shifted from 600 to 1000 kilograms per hour to around 200 to 600 kilograms per hour. So this indicates that the wavelet method has a higher sensitivity to so-called weak plumes, thus achieves a lower detection limit in methane air data. And the lower right figures here show two specific examples where both methods detect the plume in figure A. The flux here is around 1000 kilograms per hour, but the plume in figure B with the flux of 600 kilograms per hour was not only detected by the wavelet method. So the table here summarizes the number of true detections and false detections for each method. So the wavelet method generates 181 false positives, which is not a very small number, but it's also significantly lower compared to the DI method. And the wavelet method also missed 48 plumes detected by DI. So let's take a look and see why this happens. So starting with the false positives, so among these 181 false positives, about 46% were due to the background interference, such as the effects of nearby emissions, surface heterogeneity, clouds, or instrument noise. So in the top panel, figure A is an example of this background interference. And this suggests that even though this wavelet denoising step reduces background variability, it doesn't actually completely remove it, especially when we apply the method over an entire scene. Here, one promising future direction is doing adaptive region-specific parameter tuning to better account for those different background conditions. And I will go back to this idea in a few slides and discuss this in more details. Another 42% of the false positives were from diffuse enhancements. That is emissions that are not source localizable. So this could come from either the dispersed small emissions below the detection limit, or it can come from intermittent sources that stop emitting before the overpass, or it can be eddies and turbulence that fragment a plume into detached clumps downwind. So in the top panel, figure B and C are two examples of diffuse enhancements. B here is probably area emissions, and C here is probably a fragmented plume. Next, we also examine the 48 plumes missed by the wavelet method. So here, by saying false negatives, just want to clarify here that these are relative to the DI detections, since we don't have, the ground truths for the actual number of plumes in each scene. So here, 58% correspond to the emissions with limited number of elevated pixels, or in other words, with small plume size. And in such cases, the wavelet denoising suppresses the true plume signal by treating it as noise, and thus, misses the true plume. And another 24% occur when a plume is located near a much stronger one, like figure B in the bottom panel. So in this figure, the plume in the center of the image is not detected because there is a much stronger plume in the same scene with fluxes of tens of tons per hour. And the presence of such strong plume raises our concentration threshold in our concentration filtering step. Thus, this filtering step filters out the weaker methane enhancement. And to address these problems, one potential improvement is to adopt less aggressive denoising or thresholding in high probability regions. And by high probability, I mean regions where the plumes have already been identified in previous observations or where known oil and gas infrastructure exists. And again, I will talk more about this in a few slides. And finally, one additional less common factor now written here is that sometimes the concentration map was updated by upstream processing, and we added some additional screening when the wavelet method was applied. And this screening could partially remove plume pixels, making the plumes harder to be captured. And an example here is in figure C of the bottom panel. So these are a summary of the MethaneAIR results, and here comes the results for MethaneSAT. Similarly, we apply the wavelet method to 24 MethaneSAT scenes and compare its performance with the DI method. So the left figure here shows the number of true and false detections produced by two methods for each scene. In most scenes, the wavelet method achieved an equal or higher number of true detections and a lower number of false detections. The right figure here shows a similar flux-based comparison, where we again observed a higher contribution of the wavelet method to the low volume emissions. And this slide shows a concrete example from a MethaneSAT scene in the Permian Basin. So in this scene, both methods found 4 plumes, which are shown here in the zoomed in view with white borders. And the wavelet method found additional 13 plumes. And in terms of the flux magnitude, the estimated flux here generally range from 1 to 10 tons per hour. And the lowest rate is about 760 kilograms per hour. The highest here is nearly 16 tons per hour. And again, some false detections analysis. So in general, we observe more false positives in MethaneSAT data compared to MethaneAIR. This is mainly because of MethaneSAT's higher sensitivity, which makes diffuse enhancements more visible and more frequently detected. In this case, about 65% of the false positives come from diffuse enhancements. Here you can see 2 examples. A here is probably area emissions or possibly from an intermittent source. And B here looks like a fragmented plume to me. As for missed detections, the wavelet method misses 2 plumes in this dataset compared to the DI detection. So similar with what we saw with MethaneAIR, these two missed detections are influenced by the presence of a much stronger plume in the same scene, which makes the weaker plume signals harder to be detected. And this slide shows us another additional challenge that we observe in both MethaneAIR and MethaneSAT, which is the emissions from nearby sources, they merge together as they move downwind. And our model tends to group these merged plumes into a single mask. So in this case, because we don't have a very good idea to separate these, especially in our quantification method, so we treat the combined plume as a single source and quantify the total emissions from both sources together. And some of you may also wonder about the detection limits of MethaneAIR and MethaneSAT with the wavelet plume detection method. So here I want to refer to another work we did, which was led by a grad student of the group, Ethan Manningham. The paper is now in preprint, so feel free to check it out. The goal of this study is to develop a probability of detection model to allow for direct comparison between different observing platforms and different detection methods. The model here is trained on simulation data and then validated on control release data. And what we see from the left figure here is a cumulative emission rate distribution. The two colors here represent the wavelet detection method and the DI detection method. The difference between the solid and the dashed line here is whether the distribution is weighted by the probability of detection, or PD. So what we see here is that the wavelet method consistently detects a larger number of low emission plumes with or without this PD weighting. Thus leads to a less heavy tail distribution. Also, this paper implies that the wavelet method is more robust to the real-world observations compared to the DI method. And by real-world, I mean the observations that usually have issues with missing data. And the figure on the right shows the PD of different emission rates and different wind speeds for MethaneAIR and MethaneSAT using the wavelet method. So what we can see here for MethaneAIR, for example, for an emission rate of about 1,000 kilograms per hour, the wavelet method achieves a PD of about 0.9 at wind speed of 1 meter per second, and then it drops to about 0.3 and the wind speed of about 10 meter per second. For MethaneSAT, for example, if we see the emission rate of 2,000 kilograms per hour, then the PD is about 0.85 or so at 1 meter per second wind speed. And again, it drops to about 0.35 or so at 10 meter per second wind speed. Finally, I would like to highlight a few directions for future work that we think are worth exploring. First, targeted denoising in subregions. I kind of touched on this earlier when discussing false negatives. So recall that our model sometimes miss weak plumes, especially when there is a much stronger plume in the same scene. So one way to improve the sensitivity to weak plumes is to leverage prior information, such as the locations where plumes have been identified previously or where known oil and gas infrastructure exists. In these regions, we can use less aggressive denoising and thresholding to make sure the weaker methane signals were not suppressed or filtered out. And some external data sets can be potentially very useful here. For example, the UNEP's IMEO dataset contains the plume observations from many platforms, and also some oil and gas infrastructure geospatial databases. The second direction here, also kind of briefly mentioned this earlier, is to conduct adaptive and region-specific threshold tuning to better account for background heterogeneity, noise characteristics, and wind conditions. So we have already replaced some background, some parameters that we initially use as uniform values across the scene with region-specific values that take background heterogeneity into consideration. And the improvements were obvious. So we are working on testing other adaptive strategies to further increase the sensitivity of the model. That said, both approaches come with a trade-off because increasing the sensitivity can also lead to more false positives if not handled carefully. So a third direction here is to develop false positive classifiers targeting specific artifact types, such as the surface albedo effects and diffuse enhancements. And actually, such work have already started, led by another grad student in the group, Raya Altenheimer, who very generously offered me this summary slide. So basically, what we did is that we first developed a polynomial distribution for both the methane concentration layer and the albedo layer. And then we use a simple random forest model to classify the plume labels into true or false categories. And by applying such model to MethaneAIR data, we observe a really good performance on detecting albedo artifacts. And we are extending the scope of this study to include more false detection categories, especially diffuse enhancements. Okay, so here's my final slide. So some takeaways. The proposed wavelet method is an automatic methane plume masking method that reduces manual inspection by largely decreasing the number of false detections. It also shows higher sensitivity to weak plumes that are more often missed by conventional techniques. And because this method is image processing driven, it is expected to be transferable to a wide range of platforms and use cases for methane or other trace gases with plume-like structures. And here, I also added a few other work in our team that falls into the point source domain. So for example, these probability of detection analysis already touched that. So if you're interested in the detection capabilities of MethaneAIR and MethaneSAT, I encourage you to check this paper out. Another very interesting work led by our colleagues in New Zealand Space Agency focused on these agriculture methane plumes using MethaneAIR data and the wavelet plume detection method. Also, our colleague, Professor Louis Gonter, has recently published a paper focusing on MethaneSAT's super emitter detection. And in his paper, he also compared to retrieval, the CO2 proxy and the matched filter. So if you're interested in the difference between these retrievals, I encourage you to check this paper out. Also, some ongoing work. So for example, this machine learning-based plume detection, I've also involved with this work. So currently, we are exploring instant segmentation models using the methane concentration maps as inputs and the wavelet labels as training set to train our model. Currently, the architecture that works the best is the mask RCNM with ResNet 50 as backbone. And we've seen pretty good detection accuracy. And also, the scope of this study will be extended to include L1B data as input data. The false detection classifier already touched that, and with more to come. And just this morning, I've also added a recent MethaneAIR 2025 data set. So if you're interested in more data of our observing platform, feel free to check this out. So the data were produced using the wavelet plume detection method and the DI quantification method. Okay, with all that, this is the end of my talk. Thank you all for listening again, and I'm happy to take any questions.